Okay, all right, so that's happening. It takes it a second to gen up. What time, are we on time or we're 4 minutes behind? I didn't think I was chairing the session, so I didn't do any type of introduction. Phil needs no introduction, so he will not get one. my go-to response there. So, Phil, why don't you just go ahead and share your screen and start?
Okay, I'll do that. Good afternoon, everybody. Can you all hear me and can you all see my presentation?
Yes.
So I'd like to thank the organizers for allowing me to give a little bit of an insight into DLSRs in general. So the beginning of this first half or so of this talk will be quite didactic. And then I will continue with some highlights of science at the Swiss light source, which we use as our justification for upgrading our synchrotron to a 4th generation diffraction limited storage ring. Okay, so let's get started. Excuse me. All right. So I'd like to just begin with a little bit of an introduction about what synchrotrons are. I'm assuming most everyone here knows that, but it doesn't harm to give an extra couple of minutes. And then what really differentiates the 4th generation DLSRs, diffraction limited storage rings, from the 3rd generation, and what we intend to do at SLS2 with some science drivers. Okay, so what is a synchrotron? I think many of you may have seen this schematic before. In any case, I want to break this down into an electron gun and a linear accelerator, which will accelerate the electrons inside a vacuum up to several hundred mega electron volts. And then these are ramped up in a true booster ring synchrotron to the storage ring energy, which is typically measured in a few giga electron volts of energy. These electrons are then injected into the storage ring. And one sees, therefore, the path of the electrons here. Now, the electrons are forced into a closed orbit by sets of bending magnets, plus other electron optics, which I do not want to go into detail right now. And in between, and these are actually the important things which will now, how these are designed, which differentiates diffraction limited storage rings from 3rd generation sources. It seems quite mundane, but you will see why in just a moment. Anyway, in between these bending magnets, we have the insertion devices, and these insertion devices in general produce the most brilliant radiation. Not all synchrotron experiments want to use insertion devices, but most do. Insertion devices are straight devices in which the north and south poles alternate from up, down, up, producing, therefore, a slalom path for the electrons as they pass through that. Okay, and then the radiation then comes out from the synchrotron through some kind of X-ray window onto your beamline where you do your experiment. Okay, so I think everybody's probably familiar with that introduction of what a synchrotron is. But who uses synchrotrons? Well, nowadays, very much different from maybe 30 years ago, in which synchrotrons were dominated by physicists and to an extent physical chemists. Nowadays, I would say the majority, and one certainly sees it here, and this is taken from 3 large synchrotron facilities from across the world, the statistical data. It's actually dominated by the life sciences and material sciences. So what does one look for when using synchrotron light or X-rays in general? Well, in general, one would like to have a very intense beam of radiation, and one would like that radiation to be parallel as possible, not going in all directions. It should be a pencil beam. We would like the source of that radiation to be as small as possible, and we would like for there to be a fine band, narrow bandwidth of radiation that we can select. So the flux is generally defined as the number of photons per second for a given bandwidth. And traditionally, at synchrotrons, this is defined as a 0.1% bandwidth. So if, for example, one has a 0.01% bandwidth, which is about what one has if one uses a silicon 111 monochromator, then however many photons per second you have to multiply by 10 to get 0.1% bandwidth in order to get your flux. The emittance describes how parallel and how tight the source is of your radiation, and is expressed in millimeters squared source size and milliradian squared divergence in the two orthogonal planes. And one can then bring all of these concepts together in so-called brilliance, which is simply the flux divided by the emittance. The higher the brilliance, the better your synchrotron facility. So if one looks at brilliance as historically since the turn of the 20th century, one sees that not a lot changed for about 50 odd years until the introduction of the rotating anode. Now this y-axis is logarithmic, so you see that this very modest increase here does correspond to about a factor of 10. But things became extremely more brilliant when people started to use synchrotrons parasitically in the 60s and 70s. These facilities were in general used for high energy physics, structure of atomic structure experiments, but synchrotron scientists used these parasitically. And it wasn't until the 80s that dedicated synchrotrons were built, and in 1994, officially, the first third generation facility at the ESRF in Grenoble was inaugurated, which featured these insertion devices, in particular, undulators. Now, in about exactly in 2009, the first photons came out from the LCLS in Stanford. And this produced a jump in brilliance of several orders of magnitude, typically around 9 or 10 orders of magnitude. And this increased instantaneous brilliance is so high that the kind of experiments one generally does with XFELs differ certainly, if not in quality, in practical aspects, because the radiation tends to obliterate the sample within the time it takes for that sample to actually impinge on the surface. However, more recently, starting with MAX 4 in Sweden, and now continuing with the Sirius light source, and most recently the ESRF in France, they did an upgrade of their third generation facility. We now have DLSRs, which to an extent fill the gap between the third generation and the XFELs with regards to their brilliance. Should just be noted that the increase in brilliance far outstrips the well-known Moore's law of increase in computing power, which goes up about once every 18 months or thereabouts. This gradient corresponds to about once every 14 months, a doubling. Okay, so what is a DLSR? What differentiates a DLSR from a third generation synchrotron facility? Well, while the third generation facility concentrated on the amount of photons being produced by the insertion devices, also how narrowly they were emitted, the fourth generation really concentrates on these emittances. In other words, the size of your X-ray beam and its divergence. But how is this achieved? Before I go into any details here, it's worth just summarizing aspects of emittance. Now, the total emittance is in fact, this is shown here in green, is in fact a convolution of the electron emittance, which I show in blue, and the photon emittance, which I show in this golden color. And one sees that these add up in a kind of Pythagorean manner, in order to obtain the total emittance here. Now, the electron beam emittance is constant around a ring, but is a function of the storage ring design. So if you design a storage ring poorly, you will get a poor emittance, but that emittance will stay the same all the way around the ring for the X plane and for the Y plane independently. So the idea obviously there is to produce as good an electron beam emittance as possible. The photon emittance, on the other hand, this is the emittance due to diffraction effects, and this is a clue to the D and DLSRs. It's also called the single electron emittance and is a function only of the photon energy and is equal in both the X and Y planes perpendicular to the direction of propagation. And it emerges that the root mean square standard deviation of the size of the photon emittance is given by this expression here, and its divergence by this expression here. Now, the emittance, as I said, is just the multiple of the source size and the divergence, and this results in a very simple expression that the emittance due to the photon emittance alone is simply lambda divided by 4 pi and is absolutely invariant for a facility. Okay. Now, like I said, Liouville's theorem says that for a given storage ring, the electron emittance will remain constant. Nonetheless, that emittance can be juggled about a little bit. Do we want to have it as a very, very small beam with a larger divergence, or do you want a larger cross-section and a narrower divergence? And the ratio of the source size to its divergence is given by the so-called beta function. If one therefore has a large beta function, one has a larger source size and a more parallel beam, and a small beta function is associated with a small source size and a more divergent beam. And instead of showing it in the form of beams, one can show it in so-called phase space, where on the x-axis, the source size within a given plane is shown, and on the y-axis, its divergence is shown. Now, be careful here, although I've just explained that clearly, do not get confused by this being simply a cross-section through your electron beam. This is not the case. This is the source size versus the source divergence. And both the x and the y axis, the x and the y direction of your electron beam will have its own phase space ellipse. Now, the area of this ellipse remains constant due to this relationship here, but the aspect ratio can change according to whether it is a large beta function or a small beta function. Okay, so if we have a well-matched facility, then the shape, in other words, the beta function of our photons and our photon emittance and our electron emittance are identical, preferably, or at least similar. If it is poorly matched, then we have the different case where the total emittance is considerably larger because we have not matched our photon and electron emittances. Okay. As I say, the photon beta function is simply a constant number. It's just L divided by 2 pi. L is the length of your undulator. I concentrate here on undulator emittances. It's a little different and more fuzzily explained for bending magnets, but the principles remain the same. So for a given, actually for any facility, the shape of the photon emittance is completely fixed, simply given by L divided by 2 pi for a given length of an undulator. Okay, so what happens then at a fourth generation facility? I have here the total horizontal emittance plotted as a function of photon energy for 3 different photon energies, starting at 300 electron volts, 3000 EV, 3 kV, and 30 kV. If we run this out, we will see if we change our beta function, how things change here. So what we see here is that the photon emittance continues to play a significant role here at low photon energies. Whereas at high photon energies, the photon emittance is so small that it's completely dominated by the electron emittance. And one actually sees, therefore, that the electron emittance at high energies is completely dominated by the electron emittance as shown here. Things do not change very much. It's only at the lower energies where things really change significantly. And one sees actually that there is a minimum here. If one looks at the blue curve, it starts and it goes down and it hits a minimum. And it hits a minimum there exactly at a beta E of 0.16. And that is simply equal to 2 divided by 4 pi. So 1 divided by 2 pi, L divided by 4 pi, excuse me. Okay. So in a third generation facility, let's say something with an electron emittance typically of around 5,000 picometer radians, 5 nanometer radians, then we see that the best match is for sigma E is equal to 28 microns, sigma E prime 177 microradians, and one sees the relationship between the electron emittance and the photon emittance. But having said all that, who really cares? Because we really see that the electron emittance dominates in all cases. So having a good match here makes a bit of a difference, particularly at the low photon energies. But at the high photon energies, it really doesn't matter if this little yellow ellipse here is pointing upwards or pointing in a horizontal direction. So, but you would really have to have a terrible mismatch for it ever to have any significant impact. Okay. In the fourth generation, however, we see a completely different set of conditions. We see for the low energies that, in fact, we're completely dominated by the photon emittance. And at a couple of, about 1,000 electron volts, they're very similar. And up at 1 angstrom, or 12.4 kilovolts, we see that the electron emittance dominates, but it's not so dominant like it was for a third generation facility. And if we see how this emittance changes as a function of, how the brilliance changes, how the total emittance changes as a function of the electron emittance. If we're starting here at 5.5 nanometer radians, and we're going to go down to around 100 picometer radians, and again, we've selected these different energies here. We see this is how we are, where we are to third generation facility, and we see as we go down that things really start to make a big difference once the electron emittance becomes comparable to the photon emittance. We see here for the low energies that after a certain point, the photon emittance absolutely dominates and controls the total emittance. And in this case here, they become very similar, but only right at the end. So what we generally have worked out from this is that in diffraction limited storage rings, it becomes possible that the photon emittance starts to determine the total emittance. It becomes a significant fraction of the total emittance. And the differences which are seen are significant, most significant in the hard X-ray regime, where in the past there had absolutely no impact at all. Suddenly it becomes more important. So how do we actually improve our electron emittance from what we have normally had in the third generation to what we will now have in the fourth generation? Well, it emerges that the electron emittance is a function of the angle subtended by one given bending magnet, shown here in blue. So if we have, for a given arc sector, only 2 bending magnets in a so-called double bend achromat, which was the standard magnetic construction for 3rd generation facilities, and replace this with many smaller bends, which have a much narrower subtended angle per bend, per dipole, then the emittance goes down by a significant amount. And to be precise, it goes down by this expression here. Note that it is proportional to the square of the storage ring energy, gamma, and to the cube of theta. So if we take a ratio of the electron emittance from a double bend achromat, which one would find in a 3rd generation facility, to that of a multi-bend achromat with m dipoles per arc, we find out that this ratio is given by this expression here. So if we take a value of m equals 7, which is the value taken at the ESRF and also at max 4, we end up with a ratio of the double bend achromat to the 7 bend achromat of almost 100. So we have improved our electron emittance by a factor of almost 100, simply by dividing up this double bend achromat into a set of 7 smaller bends within the arc. So in summary, DLSRs make the electron and photon emittances comparable. This is why they are so, this is what makes a difference between 3rd and 4th generation facilities. So if one looks, for example, at the if one looks, for example, at 3rd generation facilities and 4th generation facilities in orange and in blue, respectively, you see that things improve typically by a factor of 10 to 30. One last thing before we get on to real experiments, which are done at the SLS and some of the statistics. Coherence. Coherence is an extremely important property emerging in many imaging techniques at X-ray facilities, at synchrotron facilities. One can consider coherence to consist of, well, initially one may have a rather broad polychromatic source, and one can make that more parallel by using a pinhole, and one can also insert some kind of filter, such as a monochromator, in order that there is only a very narrow band of radiation that is produced. The pinhole will improve the transverse or spatial coherence, whereas the longitudinal coherence is determined by the relative bandwidth delta nu divided by nu. So the transverse coherence increases with reduced source size and reduced source divergence, which in other words means that there's a reduced emittance. And one can calculate how the coherent fraction improves as one goes from a 3rd generation facility to around 5 nanometer radians to a well-matched facility at 50 picometer radians. Again, I run through the video and I leave the 3rd generation there as a comparison. And one sees the electron emittance going down, now 2000 picometer radians, 1000, and now moving down to 50 picometer radians. And one sees that the coherent fraction was very good for 10 electron volts right on the left-hand side, but has only improved by a factor of about 1.5. Whereas on the right-hand side, it has improved by a factor of 100. Okay. One could ask, well, then, if the coherent fraction is so good at soft X-rays, why don't we just stick with a 3rd generation facility and use the soft X-rays at a few tens of EV? Well, the reason is pretty obvious. The interaction of the X-rays is so strong with matter that imaging is essentially impossible. And one needs to use hard X-rays in order to do certainly transmission imaging and even reflection imaging past a couple of nanometers depth. Okay. So facts and figures about the Swiss light source. So the Swiss light source had first light in April 2001. And since we first got the digital database online on 2006, we have had over 55,000 user visits and approaching now 750,000 hours of user beam time. We have discovered 750,000 PDB structures, which have been deposited since 2002. And one must also consider that there are industry protein structures of about 3 times that amount, which have not been made published, because they are, of course, commercial in confidence. This gives a little plot of the publication, the cumulative publication count at the Swiss light source for different impact factors. So what's the difference between the SLS and SLS2? Well, we've gone a little bit up in storage ring energy. And you may remember from a couple of slides back, I said that the emittance is actually proportional to the square of the storage ring energy. So one would perhaps think, okay, we don't want to go up in that because that's going to increase the emittance. Now, going from 2.4 to 2.7 is a fairly modest increase and will not impact the emittance very much just with regards to this ratio. And what 2.7 gigaelectron volts does allow is for us to access higher photon energies. And we're a medium energy storage ring and only a small circumference of less than 300 meters. And we would really like to access the many tens of kiloelectron volts leading up towards 100 kiloelectron volts. And this will help in doing that, particularly in conjunction with the use of some interesting new developments in the source technologies, namely superbends running at around 5 Tesla, but also we are developing a superconducting undulator with a 10 millimeter period, and I will talk about that in just a moment. The current will remain the same. We'll have 0.4 of an amp, and the achromat type will go from what we actually had was a 3-bend achromat, which at the time of 2000 or thereabouts was quite revolutionary, to a 7-bend achromat with something called reverse bends. I do not want to go into the details of these in this lecture, but this has helped improve our emittance by about a factor of 2, which is an important feature for this small circumference ring. And the predicted horizontal emittance will go down by a factor of 35 to 157 picometer radians. Importantly, we will also use not just 9 of the 12 straights, which we presently do, but 11 of the 12. The 12th one we cannot use because this is where we inject the electrons in from the booster ring into the main storage ring. So that's used up for that. So this is what a schematic of what the beamline portfolio is. A little bit of background to this. The beamlines which stay where they are shown in green with the lettering, I should say. The ones which move are shown in this purple color, and new ones are shown in red. The kind of source we have are given by this these lines here and these circles here. Boldface indicates that there's a major upgrade of the beamline during the project. A lot of the upgrades will actually be funded outside of the project. So we are investing the money which we've obtained, obviously, in getting a good ring going and then making some flagship beamlines. And then the remainder of the beamlines will be funded from outside the project itself. For those of you who are interested in looking at this in detail, feel free to look or even download the CDR of the SLS2 beamlines at this link here. Now, in order for you to understand a little bit more what the names of these beamlines actually correspond to, I show a list here of the beamlines covering the energy range. For the soft X-ray beamlines, there is a nice to have regime and a must have regime. And we're still negotiating a little bit as to how far into the red region we will go with the insertion device group and the magnet group. But it doesn't change the fundamental information behind this. So I won't go into all the details here as to what each beamline does. I would like you to do that perhaps in your own time. I just would like to say is we have a couple of bending magnet beamlines. So all bending magnet and super bends I show here with a thick border, and the super bends are highlighted in green, the normal bends highlighted in blue. Okay. And briefly, I just flash up here the brilliance curves for the different sorts of undulators shown here, and bending magnets and super bends shown here that we will use at the at SLS 2.0. There is a little bit of negotiation still underway as to whether we will use either the cryogenically cooled permanent magnet undulator with an 18mm period or 16mm period. And in fact, we are tending now towards one with 17mm, but one sees that would squeeze in between this cyan and this blue set of curves here. The information you obtain is essentially identical. What is quite interesting, however, is this high temperature superconducting undulator with a 10mm period. And I will talk about that in just a moment. So our electron emittance will improve by around a factor of 35. And we hope to get first light in 2025. I'll talk about that in a moment. But let's not forget that the brilliance is not just all about the emittance, which I've just said improves by a factor of 35, but also about the flux. And we're making a lot of effort to improve the quality and performance of our sources, particularly our undulators. And indeed, if we look at the ratio of some of the most important parameters, brilliance, flux, coherent fraction, and coherent flux, as a function of photon energy, these are factor improvements, right? We see that in the case of brilliance and coherent flux, we are improving things by about a factor of 1,000 in the hard X-ray regime at 20 keV. And indeed, I only show it up to 20 keV because we don't really have, we have some decent data for 30 keV, but we certainly do not have decent data for 60, 70 keV. And in this regime, our factor of improvement is essentially infinite because we're now going to photon energies which we could never have accessed before. Now, this on the one hand is due to long undulated, long high K. So yeah, I don't want to go into details what high K means here for those of you who are not in the know, but it means you have a slightly stronger magnetic field. Undulators which are up to 3 meters in length and are made out of modular sections. And that's already almost double the length. In fact, I think it is double the length of the longest undulator we have in the X-ray regime at the moment. These are used in the hard X-ray regime, as indeed is this. And this is a 10mm superconducting undulator, which we are doing an R&D program with the Fermi laboratories in the US. Okay. So a little bit about the timeline. This is today, this red line here, and we've secured the funding, we've defined the lattice ring and the beamlines and their positions, and we're in the process of making sure all the magnets will be, the magnets we designed, that they work properly, and the new chambers, the vacuum chambers which we have to use for the electrons within the storage ring all operate properly. And we have a little less than 1 year to really have a go, no-go moment. In other words, we will say, okay, at the end of September 2022, are we going to go ahead and really tell all our users that they can stop doing experiments 1 year later, or will we have to shift everything back? So far, we're still on schedule. So the dark time will begin on the beginning of October 2023, and will span 15 months of the tunnel being closed, and actually 18 to 21 months until beam becomes available and commissioning of the beam lines can start. And user operation is predicted to start in mid to late summer 2025. Now, we do not have the necessary resources to get all the beam lines, particularly the insertion device beam lines, up and running from the get-go in 2025. And as a result, the soft X-ray beam lines, the insertion devices, most of these, with the exception of one beamline, the SIN beamline, which will be installed in the first round, all the others will be installed in this second shutdown lasting around 6 months, which means that full user operation across the board should begin again in summer 2026. I'd like to finish now with some showcases of science opportunities which we have identified at SLS for SLS 2.0. I should perhaps begin with what, of course, is of interest to everybody worldwide, and that has been the COVID pandemic. These are just 3 examples of some of the, I'm sure why he wasn't rotating, some of the proteins which were investigated and their structures discovered in the development of a novel COVID drug. The structure of the virus protein PL-PRO, which is the papain-like protease, was identified as a possible target for future drugs. So needless to say, although we do have vaccines, the research into this is still continuing and extremely hot area of research. I invite you also to look at this link here on our general research on COVID. This also includes not just protein crystallography, but also nanoscale and micron scale imaging. And this, for example, is a tomogram of a complete rat lung, or in fact 2 rat lungs, with 2.7 micron resolution. And this corresponds, even for a rat, which isn't that big, to 600 gigavoxels of information. We are obviously involved in fragment screening as well. One has to be for this kind of research, and this is shown schematically here. We, of course, have used robots all the time in order to get through as many samples as possible. And we're talking really about 10 to 50 samples per hour at the moment. Now, the PX beamlines, the protein crystallography beamlines at SLS2, there are 3 of them. We have our flagship beamline, which goes from here to here as regards performance. This is the triangles. We have our commercial beamline, which will go from here to here, and our superbend beamline, which will go from here to here regarding flux and beam size. So all of them reduce significantly their beam size, and the flux goes up in all cases, most notably in the case of, sorry, I should say that there are 2 modes of operation according to whether we use a multi-layer or silicon 111 monochromator. And so but in all cases, we have a significant increase in our flux by around an order of magnitude. So the idea here is to really be able to do conventional crystallography at unconventional speeds, so about 1 second for an entire diffraction data set using the most modern detectors and these very powerful beams. We would like to start to use crystals down to around 1 micron in size in serial synchrotron crystallography, and would like to identify dynamics down to around 1 microsecond in time-resolved serial crystallography. It's nearly always serial crystallography. And then lastly, using particularly low energy single anomalous diffraction, we hope to be able to identify anomalous signal down to the level of around 1%. So as far as drug discovery and fragment screening is concerned, crystal growth has really reached something of a stasis, and the industry would really like to do more with their less perfect samples which they provide. And the newer synchrotrons really allow one to identify, to use these very, very small crystal crystal sizes around a micron or even less. One can either use a jet or a toothpaste, or perhaps a fixed membrane. And this is a little movie here showing acoustic levitation of a small crystal here, just slowly becoming stabilized inside this acoustic levitation setup here. Now, the requirements one needs for fragment screening is that we really need to know what the precise location of these fragments are and their orientation on a large biological target. So we really need 1 angstrom resolution or better. And we need fast throughput, hundreds of samples. And presently, I've written here 50 plus fragment samples per hour. As I say, we're closer to 50, or sorry, 30 plus I wrote here, we're closer to 50. The bottleneck seems to be the length of time it takes for structural solution. And we hope to overcome this by use of off-site supercomputers, among other things. Now, these crystals can be very small, and indeed, membrane proteins and GPCRs correspond to around 1/3 of all proteins, and so far, around 2/3 of all drug targets. But because they're hydrophobic, they are very difficult to crystallize, and often produce crystals only of the order of about a micron in linear dimension, which makes them difficult to handle. So in order to really look at these very, very small crystals, we need small and parallel beams and high intensities. And this is exactly what DLSRs provide and what we hope to be able to provide at the SLS. Note that because of the automation, from 2025 onwards, we predict that we will be producing around up to 100 terabytes per day. This is an enormous amount of data, and this is a whole problem of it on its own, which needs to be addressed. So in serial synchrotron crystallography, one has this jet of crystals which we hit with our synchrotron. We may also be looking at dynamics and looking at maybe photo excitation using some sort of laser. And then we get our diffraction pattern at some random angle, some random orientation on our detector here. And one can collate all of this data one after the other, and then in the end produce a full diffraction pattern, which may require over 1 million individual diffraction patterns at random orientation. But in order to achieve this, we really need the high brilliance and flux, which the SLS2 will be able to provide at the PX beamlines. Now, with regards to low energy native SAD, as I mentioned before, the 1%, we really want to be working around this area here, somewhat past the sulfur edge. Sulfur is the go-to element for native SAD. Now, of course, we can't really work really below the sulfur edge because the absorption is just too high. And even at the absorption edge, one has a lot of problem with vacuum, having to put everything in vacuum to avoid absorption. What I show here is the anomalous signal as one goes up in energy. Maybe I'll just rewind that a little bit. So I'm going up in energy here, and we come to the sulfur edge here, and then suddenly the difference in intensity of Friedel pairs goes up enormously, and one gets a very strong signal. But even at higher photon energies, and we'll see it's moving up now, these little circles here, we still get significant signal, and we can even do good quality SAD measurements up at several thousand electron volts. I'd like to move on to now more conventional imaging rather than crystallography, and this is where coherence really comes into its own. So the CSAX beamline has really been a trailblazer in X-ray so-called tychography. This is this term here, tychographic laminography and tychographic tomography. This little video here, which I'll show in more detail in a moment, looks at the Intel chip, an Intel chip with around 22 nanometer Intel chip structure architecture. This one here is also a beautiful example of a mouse brain with over 5 teravoxels of information, where individual regions have been investigated, and then these have all been stitched together using a very sophisticated software in order to look at the entire mouse brain. This was reported in 2019. We also are very much involved in fast tomography, and indeed we are now capable of recording 1,000 tomograms per second at the TomCap beamline. Now this really means 1,000 tomograms, and tomogram requires half a rotation of the sample, and in that half rotation one would record about 100 or 200 images. So one is really talking around 10 to 20,000 images being recorded per second in order to look at these sorts of processes, such as here, bubble nucleation and evolution in metal foams. In some cases, we are not really any longer limited by the frame rates at which we capture, but more the centripetal forces acting on the sample. If it's a soft sample which is easily distorted, and that distortion can produce artifacts in the dynamics, then we're limited by that. Also, we are working in the soft X-ray regime in reflection mode. So at the SIM beamline, they were working on the Cobalt L edge and looking at gigahertz dynamics of these magnetic domains using XMCD, X-ray magnetic circular dichroism, and tychographic tomography. And we intend to pursue imaging at these beamlines, which I've shown here, these hard X-ray beamlines in blue, the soft X-ray beamline SIM, and in Phoenix, although they actually haven't started yet, this spans the soft to hard X-ray regime, crossing the tender X-ray regime. So tychographic nanotomography has really been something where we have led the world in the as regards X-rays, and this is will only become more so with the improvement in the coherent fraction. So lenthless imaging in general is simply looking at the speckle produced by scattering, elastic scattering of a sample. And tychography, well, okay, maybe a step back here. When one records a scatter pattern, a speckle pattern here, one records the intensities and the phase information is lost. This is always a ubiquitous problem for X-ray scattering techniques. So how does one go about regaining these this phase information? Well, in the case of tychography, one simply moves your sample to a new position which significantly overlaps with the old position. This means this overlap region here, whatever you use for your phases associated with the speckle pattern, if they are correct, then clearly whatever comes out from the inverse Fourier transform needs to be identical in this overlap regime. So this is a very, very strong boundary condition. So one can go through iterative procedures until all of these this phase information becomes consistent. So we're using this. One can actually look at samples over many hundreds of nanometers in extent, and with, even hundreds of microns in extent, with resolutions down to a couple of tens of nanometers. In fact, we've even gone down to under 10 nanometers resolution. Now, laminography is just a variation of tychography where the sample is flat and thin, a bit like a leaf, or in this case, a silicon chip. If one were to have this around some sort of symmetry axis, at one point during the rotation, you will have suddenly a very much larger absorption than anywhere else. So if you imagine this silicon chip being vertical and one spins it around its vertical axis, when that silicon chip is just online with the incoming radiation, then that has to go through the entire width of that silicon chip, so across it along this full length here. But if one tilts the axis, one is able to record all the data with reasonable transmission. And this is what was done in the case of looking at this 16 nanometer technology, image using laminography, tychographic laminography. And this was published in Nature also in 2019. Okay. This was cryotachographic tomography was also used to look at Parkinson's diseased brains and how these differ from a healthy brain, particularly with respect to the swelling along the axons and neuromelanin containing organelles here, and these are color coded. For more information, I refer you to this publication here. We've also done magnetic tychographic imaging in the hard X-ray regime. This is shown in these publications here. This caused quite a stir in 2017 and made a few science headlines. Okay, I think I've already mentioned this in a little bit of detail. In order to do this high contrast tomography of soft matter, one really needs to use phase contrast tomography, in which the coherence becomes an important property. And this was done using the phase contrast tomography. And like I say, this is this stitching program where individual volumes were recorded. It only took about 3 minutes to do each volume within the brain. And then these volumes were then stitched together. There were a whole 1,215 of these on a RAID array cluster. This took around 50 hours, and it was possible to look at this entire mouse brain, admittedly only with a resolution down to a couple of microns. We want to 1.2 microns, in fact, and we want to improve this in future studies. Now, in the past, this famous movie of The Fly was always used to show fast tomography, but like I say, this, although perhaps a little less sexy in the imagery, really shows the kind of speeds we are able to go at now, and this will become even more the case in the case of SLS2 with the very much higher flux, in particular when we install the high temperature superconducting U10 undulator. This is just a table of the anticipated gains of selected beamlines, which are most going to benefit from the upgrade. These numbers may have changed a little bit, but only in detail, not in quality, not in essence. So to conclude, I gave an introduction as to what synchrotrons are, what brilliance is, and why a DLSR is different from a third generation facility. I then tried to show you what improvements were associated with our upgrade and what our beamline portfolio will be. And then I finished with some highlights from the SLS, which will drive the science at SLS2. And with that, I would just like to say that a lot of the images and animations I showed here can be downloaded for free at the Wiley link of my book here, but also at this website here called synchrotronmovies.com. All of this is freely available, and I am in the process of updating the MOOC, the Massive Open Online Course, and hope to have this ready for publication towards the turn of the year. And with that, thank you very much for your attention, and I would be happy to answer any questions.
Wow, thank you, Phil. That was very nice, very nice, very nice. So I think I see a couple of questions.
Mm-hmm.
What you can do is you can use the little raise your hand function, or you can just unmute yourself and ask. Tabitha, did you have one? And Simon?
Yes, my question was regarding, very nice talk. My question was regarding the go, no-go decision point that's coming up. And I wanted to know, is it only cost that's a factor in this go, no-go? Are there other factors, and can you elaborate?
That actually is not a factor at all, the cost. We have the funding. Okay, we don't have all the funding for the beamlines yet, but we are confident that we will get those. No, it's technical issues. We are trying to squeeze a diffraction limited storage ring into a 7-bend achromat DLSR into a 290 meter circumference ring with 12 arc sectors. This is a tall order, so we have to be extremely clever in our design of the magnets in the arc sectors. This is not my area. I dabble in talking to people about it, and I kind of sometimes understand what they're going on about, but it's not my area of expertise at all.
So as a follow-up, just quickly, this brings to the idea advice for the African light source, as it has not been fully designed and constructed. Is there any, from that perspective, advice in terms of going for the MBA, the multi-band achromat, at the outset versus being outfitted with this later?
Well, I would say if you are a greenfield facility, which it sounds like you are, I don't know what else it could be. If the funding is there, I mean, it is more expensive. Let's say this. If we had built a greenfield facility to replace SLS, it would be much more cost effective than what we're doing now. Of course, it costs less than a greenfield facility would cost to upgrade the SLS, because we don't have to build the building, we don't have to build all the concrete and so on and so forth. But we're paying a lot to get the multi-bend achromats to work in this very, very small circumference ring. So if you have a greenfield facility, I would strongly recommend that you go for a multi-bend achromat, at least a 5-bend, preferably a 7-bend. And I mean, there are other facilities which are using 11-bend achromats. In fact, one of these facilities which uses the 11-bend is the AfLS, the Advanced Light Source in Berkeley. Now, it only has 190 meter circumference. So you might wonder, well, how the heck can they do it if we're having such a problem with our 290 meter circumference? And the reason is they are developing so-called on-axis injection. And this is something which would cost us also a lot of research and development in order to have that from the get-go at the SLS. So I would say if you've got a greenfield facility, try and get the funding to do it anyway, a multi-bend achromat source. And if you can do it on-axis injection, what you need, of course, is the expertise and the people there to really make sure that this is a success. But yeah, I would strongly recommend any new facility has to be an MBA.
Simon.
Hi, Simon.
Hi, Phil. I just want to recognize that you are a teacher of great flair.
Yeah,
and your slides were such a pleasure to see. and I think the content was so fantastic. You did answer my question a few slides after I asked it. I was fascinated by this figure of merit thing because it's so high. And I saw you broke it up into many figures of merit, you know, depending on what one was talking about. And I was wondering, could there be such a thing as a simplified figure of merit? And can you roll in more things into it? Because along with the better emittance and so on, also comes improvements in the detectors and so on. And I hear people talk of 5D. And then when it becomes so quick to do everything, it means the way to use synchrotrons has to be completely rethought.
Yes.
And I was also wondering about the level of preparedness of the community. It seems like the advances are outstripping at this point the imagination of the community. It's just absolutely mind-boggling. And then the last thing is, people have been asking if you're going to share the slides. And at the very end, you showed some links, which maybe would be also something we could find. And it was just some banner that came up just on your mouse on the most important one. I didn't manage to grab it.
Sorry, do you want me? I mean, wait a moment. Do you mean
the one? And really, we would love to direct students to your MOOCs. Yes, this one. I just want to grab those links. Thank you. And I think your MOOCs will be wonderful. I'm so looking forward to that book as well. But anyway, that's enough questions from me.
So maybe to answer your questions, I have to try. So it's an interesting point. So brilliance is the sort of the single number figure of merit that people tend to quote as how good their synchrotron is. But you really have to think, what is my experiment? What do I actually want to do? So if you're doing, for example, powder diffraction, you don't care about source size or anything like this. You just want to get as many photons on your sample as possible. The same, to an extent, is true, not to a full extent, but certainly to absorption tomography. You don't really want a high brilliant source. You just want a homogeneous beam and lots of photons on your sample. So, you know, it's A divided by B. It's flux divided by emittance. And just in getting a very, very high brilliance, where all of that has been produced by making a very tiny source, parallel source size, a parallel source, and with a very tiny source size, that might not be very helpful for you. You might say, okay, it's all very well, but actually I want photons. And interestingly enough, we did a little thought experiment or a little question to our users, or not our users, actually our beamline staff at the SLS, and said, if we could get a certain brilliance and all that brilliance came from either an improvement in flux or either an improvement reduction in emittance, which would you prefer? And then nearly everybody said, oh, we want an improvement in flux. So, I mean, the fourth generation is going to be fantastic, no question about it. But just citing brilliance and not bothering to look into what is divided by what is a bit of a dangerous thing to do, depending on what experiments you're doing. Yeah. Your other point which you made, that things are developing so fast that we're sort of trying to catch up with this whole improvement technology, I think is completely true. There was a talk given by Harold Reichert of the ESRF upgrade, the extremely brilliant source upgrade. And he talked a little bit about this with how they assign beam time to users and how to use that up efficiently, and how all of this data needs to be put on some kind of common library and access to it. There are so many things which we're going to have to learn. It's very difficult to predict in advance what what changes actually will occur. But you're right, these 5D experiments with energy, time, X, Y, Z, they're going to be, it's going to be a whole new ball game.
Yep.
Yeah.
Yeah. Okay. Thank you very much.
I had a technical question, just, I don't know, might be kind of wild on off the beaten track, but in a multi-bin achromat environment, you're still dealing with permanent magnets. Is that correct?
Well, we are, okay, in our instance, we are using permanent magnets, and I think most of the upgrades are using permanent magnets. Up until now, we've been using electromagnets.
Right.
For the arc sectors.
What if it was possible, or if you tried to affect the bending and undulation using photonics instead of magnets? So you just you use that high laser field to
right. Well, people do this. Is this? I know people do this. Is this? Yeah, this isn't Wakefield acceleration, is it? This is something else.
So inverse Compton scattering.
Inverse Compton scattering, exactly. Now, who uses? There is a guy in California who has a company where they make these very small synchrotrons, basically tabletop-sized synchrotrons, with these counter-propagating infrared lasers, which produce these essentially standing wave undulators through this counter propagation. I can't remember what the guy's called.
It's the company's Lincian, but
yes, exactly.
But I'm not. The objective is not to make a tabletop light source.
Yeah,
it's not what I'm thinking about now. What I'm thinking about is for a storage ring solution, instead of having permanent magnets, you have laser systems to affect the bending and undulation that you want. That
would require extremely high intensities, right? In order to induce that. So we were looking at EHG as a sort of a bridge between synchrotrons and XVALs, and found that the intensities which we would be using would be were basically on the edge of technical possibilities at the moment. It's too much outside my area of expertise to comment too much on that, I'm afraid.
Right.
Yeah.
So you did mention your book, and are you're coming back to the conference to talk about the MOOC? Yes, no?
I'm in some sort of roundtable discussion on Friday, I think it is. Let me look.
I think it's Thursday.
Is it Thursday?
Or I could be wrong.
No, it's Thursday. Thursday, my time, 4 o'clock. So about this time in 2 days.
So, right. So we are having a roundtable discussion about just universities and light sources in general.
Mm-hmm.
But Dr. Wilmot will be there to talk more in detail about his MOOC, which is great to take. And the book is very nice. And the website, the total learning environment. So Thursday, what time again? I'm sorry.
4 o'clock.
Yeah. So, right. Look on the schedule. He's on there. He's going to be on there again for universities and life. So I don't know if we have any more time for questions.
All right, didn't catch that. Can you say again?
I said I don't know if we have any more time for questions right now, but let's thank the speaker. You can go under reactions and do clappings. Do with fingers. Thumbs up, fingers up. You could do, that's a raise hand, sorry. So thanks again. Thanks, Phil.
Thanks very much as well. Look forward to talking to you all again on Thursday.
Okay.
Thanks now. Bye-bye.
Bye-bye.
Bye.
Folks, we can leave this session and go to the breakout rooms. So mouse over the bar at the bottom, you'll see breakout rooms, select your breakout room.
Could I just make a quick comment? I put in the chat 2 links to an accelerator school for those of you who want to get a 2-week quick crash course on accelerators coming up in December. And I also put in the chat a website for a high school teacher workshop. And I would like to ask you to spread the word about both workshops. Thank you.
Okay. All right. I'm going over to the breakout room and one of these things. Am I chairing that session too?
I'm doing the AfLS session. So I'll
okay, I'm popping over to the AfPS. Okay, we'll see you tomorrow, Phil.
Okay.
Thanks.
I'm more than happy to share my presentation. I think it would have to be a PDF though, because the PowerPoint is a couple of gigabytes in size.
Okay, I'll get it from you by email.
Okay, lovely. I'll probably have to send that as well with Dropbox, but lovely. Thanks.
Okay, thanks.
Okay, bye everyone.
For those who wants to attend the African Resource track, please move on because the session is about to start.
Excuse me, how can I join the break room 3?
So you see at the bottom of your screen, there's something called the breakout rooms.
Yeah, I saw.
You click on it.
Yeah,
when you click on it, there is a pop-up which comes and you will sit down African Resource track.
Yeah.
You click on it, then you click on join. Once I put your cursor there, the green button which says join, it comes, then you click on join, then you are moved there.
Because I am on an African Physical Society track.
You want to go to African Physical track or you want to go to African Light Source track?
African Physical Society, I think.
Yeah, then you go there, then click on African Physical Society track, then click on join.
And then the problem is that join is not appearing when I click there.
Don't you see a blue?
Yeah, it's fine. I had to click on the number.
yeah, click there, then you see join the blue thing, then you go there. So yeah, so we expect then everyone who is here to move to those sessions. Please, those who are present here, move to one of the 3 tracks.